Hey, so what we're going to do today is we're going to go over some of the basic CNC operations, a little bit of the setup, and to do a job, and to cut some aluminum, about 1/4 inch with a couple different end mills, and go through the software, the controller, and what equipment y'all have to work with, and go over some of the existing end mills that y'all have that are assigned to particular jobs that are saved onto your computer here at Mill. So the first thing that I wanted to talk about is obviously safety. So what we have is safety glasses when we're cutting. The spindle speed can go up to, I think, about 24,000 RPM, and that's pretty fast. So it's gonna launch those chips at about that speed towards your face, and you're gonna want something to protect your eyes. It also can get very loud, so I use whatever earmuffs. There's a couple over here in the bucket next to the drill press, and those are usually there, so pretty safe bet that you'll have it there. And then otherwise, that's about all kind of protection. Besides, you probably want to do long sleeves and potentially hair back, take off your watches like in DML, and any of the jewelry that you'd have where you get caught in the spindle. Luckily, it's not as involved as a regular mill, so you're not right up against it. So you're not as close to running some of the stuff into the spindle as possible. You just set it, pray that your end mills don't break, but you step back and you watch it, make sure it's all right. So once we have these, and these are ready, we don't need that for the canning process, obviously. We're gonna move it over to the facing of the base plate. So we use HDPE as the planks, and the alternative to that is medium density fiberboard, and there's some in the shop. However, when you run your coolant, it can swell, and it can also swell with the humidity changes. So that's going to give you variations in your heights, and if that matters to you, then that's important. If you're doing a height critical part, then it's going to be offset from one side to the other side, and if you zero, you're not going to cut all the way through. So it's important to remember that. I choose to use HDPE, high density polyethylene, and that doesn't as much swell with anything, and it also doesn't swell with the coolant that we use. So it's a really nice balance. It can stay flat, and whenever you cut it, it doesn't have any of the weird features that MDF does, where it has this nasty glue in it that you shouldn't breathe in whenever it does the facing passes. So I'm thinking that the next part that we need to do is the parts. So you are using a OMIO X8. It's probably one of the best CNCs for the money at all. It's really strong for what it is. You can do decently a deep depths of cut, and your feed rate high, and it's set up with an actual spindle that you can change your speeds on the fly, as opposed to other hobby grade ones where you would have to manually adjust your spindle speed. And that's going to mean a lot later on whenever we go from different materials, different end mills, and all of those things to dial it in. So it uses a 2200 watt spindle, and it's water cooled. So we need to make sure that every time we come over here and we turn everything on, there's this little outlet underneath the table and a switch that turns it on. It's a power strip, and it gets a little bit louder. So if you want to show them that. So there's a bucket with cooling fluid in there, and I usually pull the tube out, and what it does is it just returns the coolant back to it as it goes through the spindle, and it does that loop all the way through. So if that's not happening and it's not returning, then you're not getting coolant to the spindle. It's either clogged or something like that. Don't run the spindle at that point, because it needs to be water cooled for it to work properly. So once we hear that sound, we know that the pump is running. We pull that tube out so that we know that the water's coming back through. That means we've got a full loop going through the spindle. We're pretty much prepared for everything. And we're gonna do, I don't know if we wanna face it this way, because we'll probably use the same computer, is the computer that is involved with the CNC, or it's probably going to stay here depending on what they choose. You have the laptop that has your controller software Mach 3, and you also have your actual controller, and that's going to have a lot of your, I think, stepper drivers in it, your software. Once you send anything in NC code or however it reads it to your controller, it's going to tell the CNC what to do, and then that spindle is going to go wherever this tells it to go. So we need to make sure that the VFD and the power are turned on, and I've only ever seen it for the beginning have 00 on there, but you can see a clear indication that it's on. If it's not on, then there probably was a problem and they hit this E-stop. That's going to be really important too later on, but the E-stop may be depressed, so you have to rotate it clockwise so that it can pop back out and then turn it back on. So we have the laptop, we have Mach 3, which didn't open. Yeah, it did. So Mach 3 is the controller software that your NC code interprets and sends it to the controller, and the controller sends the spindle wherever you tell it to do and whatever operation. So for the most part, CNCs are great about doing exactly what you tell it to do, but it will go all the way down into the board. It'll run into the wall if you want it to. Like if you tell it to do all of these things, it doesn't know any better, especially if there's not a limit switch or something on that side. So Mach 3 is pretty fantastic too, but it can be a little bit weird sometimes in interface because it's so broad in the amount of stuff that you can do. You've got a bunch of different tabs that you can run. This is the one that we're going to stay on most of the time, but you can switch to any of these other ones. You shouldn't have to for any of the jobs that you're doing unless you're indicating off of something. So if we need to go off of an existing workpiece, there's a special tab for toolpaths, and you can adjust some of these values, and you can tell it this, if I click it, it goes over and it can touch the side of the workpiece, and it says, okay, I know this is the left side of the workpiece. You do the same thing for this side, same thing, it knows where that is. Pretty easy center finding from there. I believe that it auto-calculates it, but you tell it what the edge finder is, the piece that you have in there, and it'll calculate the center for you. So that's really good for working off of existing work pieces. I generally don't do that. I use bigger pieces than I need to so that I can make sure that the outer edge is what I intended it to be. But if you're dealing with a limited size or dealing with a limited work piece or whatever, then you got to do what you got to do. The same thing with, you'll probably never have to work with this stuff, but the gauge block that comes with it is right here. And this is really important for setting your tool height. And that's how you recalibrate your Z. And you should always recalibrate your Z because you can't guarantee that it's in the same spot every single time you turn it on. And it may have forgot where it was. So that's very, 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 very important. Or else you can drive it into a spoil board, you can drive it into the bottom part where the extrusions are, and ruin a whole bunch of stuff. So bad news. We always do that, even if it might have accidentally done something. You're like, maybe I should, maybe I shouldn't. You definitely should. So you probably won't have to deal with anything else, but there's other parts that you can mess with. You can see what's happening. This is a very basic overview, so we're going to stay on this screen for the most part. The second part is, what's up? Oh yeah, it's great. All right, so what we want to do whenever we turn everything off, let's say like we want to kill everything. So we killed this and we close out everything on the session. And sometimes it says, do you want to remember some of the work offsets and stuff? Just say no, unless you know what you're doing. Turn on Mach 3 from nothing. And I can move this out of the way. Can you see the, all right. So let's say that we just ran a job yesterday or something like that. We killed all this, everything was turned off. We need to turn it back on. It's gonna say emergency mode active and press reset. And then that's also listed on some of the instructions on the side of the piece that somebody built for this, and then the people that are qualified. You can read some of these instructions, the main ideas, on that piece of paper, and we may expand a little bit more out of that. But the first thing that you need to do is you need to send it back to its 000 point. So we're going to press reset and then go to ref all home, and nothing's turned on. So the VFD shut off, the power shut off, and this is turned off. So that's bad. It's not moving, doing whatever we're supposed to do. We see that that's cut off. So we rotate it, open it, and we're in the middle of a cycle. So we're not gonna wanna do that. So that's something that you notice. If it's not moving when it's supposed to be moving, take a look at everything that's kind of going on. See if anything like fell out or disconnected or something like that. If there's any real big problems, we can deal with those, but let's do that over again. So we can hit reset again, and then we can almost always ref all home, and then it's going to move up to its Z0 with the limit switch. It's going to hit its X limit switch. No, I'm sorry, it's going to hit the Y limit switch, so going backwards, and then it's going to hit the X limit switch. So now it says, okay, I'm at 000, which if we go to machine coordinates, it shows 0000. If we go to real coordinates, these were the offsets that probably reflected what we ran for the last job and if it remembered things, but I don't generally trust those, so we redo everything if possible. So you can actually jog this around a little bit, especially if you need to put a new end mill or an end mill in for the first place. So we can go press tab, and tab is going to help you jog through in any one direction. You can use the pendant too. It has acted up on me in the past, so I choose to jog with the computer. The arrows that you see, left, up, down, right, those are going to jog it in whatever direction you would almost think in plane with the baseboard. So if we press downwards, right now it's in jog mode. Instead of continuous, it's in step. So we can go over to jog mode for continuous, and then now we can send it wherever we want to go. So I'm going to bring it forward. And I'm going to put an end mill in it. And the first thing that I'm going to do is take off this collet nut. There's nothing inside here. All your collet nuts are inside of this enclosure. Most of the ones that I use most often are out front, so I can continue doing it. Like the 1/8 is pretty common. I think this is the 1/4. This is a 4mm. So the 4mm collet, it'll say a number on there. Try not to trust your intuition with it, because a 4mm, a 1/4 inch is like 6.25 millimeters, and we do also have a 6mm. And if you put a 6mm in a 1/4 inch, you're going to have some slop, and then that means that you can have some damage. You can mess the end mill up. It can slide out. It could hurt somebody, whatever. So this is your collet, and then this is a 4mm. You can't really see it. I can barely see it. So let's put this back. What I'm looking for right now is a 1/4 inch. That's a 6mm, 7/16. This is the 1/4, and it does say 1/4 on it. It's a little hard to see. 1/4 is many of the baseboard spoiling ones that I use. Fits inside here, but check that out. Make sure that there's no like pieces of the MDF or aluminum or anything like that in here, so that we know that it's going to clamp down exactly how it's supposed to be. Also with the end mill, you need to check the shaft, make sure it's all good, and that everything fits the way that it's supposed to fit. And it looks like it's pretty good. Some of the end mills, or some of the collets, the collet nut can get some of the nasty stuff on the inside. You see if I tap out a lot of this. This comes from whenever we're running our cuts, it can come back up into it. if I try to tighten this down, it might not be exactly how I want to do it. So I try to clean this out as much as possible. And I do have air to spray this out with my glasses on, of course, and my hearing protection, because that's what safe people do. And now it's fairly clean in there. Some of the collets, you have to push down in and it springs in place. So you can literally like hold it by the back part and it won't fall off. Some of the other ones, I don't know if they've lost their springiness or if they weren't designed to do that, but they don't do that. These are nice because they don't fall out and all that stuff, but you have to be careful whenever you run it. The way to get these out is you could sometimes press and it pops out by squeezing it in. Other times you have to like push by the side and pull out. Sometimes it's hard. If they're brand new, they've got a lot of springiness to them. You got it. All right, so we don't put this in and then try to put this in or whatever. We put this on first. And then slide this in. And it's going to be a tight fit. That's the benefit of these collets too, is they're designed for a certain size, which is really cool. And there's a bunch of variety of sizes that we can switch for this particular collet size. So if we move this back, I can move this out of the way. And underneath, or wherever they're going to keep it, 2 wrenches that you use. And we're going to use the 21 and the 30. The 21 goes to the top part, and that's going to hold it in place, and then you slide the 30 from the bottom or however you can get onto it. Watch out for the end mill that you're using. Some of the carbide stuff is pretty tight. Oh, I'm sorry, some of the carbide stuff is pretty, can be fragile. So if you tap it accidentally or something like that, it may let go on you whenever you're doing a cut, so be careful about that. So I tighten it. I don't try to go Hulk on it, but if you just give it a snug tightness, it should be fine. So this is actually in right now, which is awesome. And we can put these back. Again, I don't know where they're gonna keep those. The board, you can see probably a little bit better now. These planks are on here, and then we're gonna surface those so that we have the same height for what we need to do. So ideally, you would edge find and you would do exactly what you need to do, as you would do in like DML and stuff, but I usually cheat just a hair. I'll go over. And then page down, takes it downwards. And I about eyeball it for this particular one, because what I'm going to do is give it an offset in the computer. I want to go past it anyway with the operation that I'm choosing, so it doesn't really make sense to take the time to zero everything out on the exact edge of it. You can do a little pseudo cheater move where you take a V-bit, and these are really sharp. So you can put that in one of the 1/8 inch collets and then find the very corner of your workpiece or whatever. And then since that's the middle of it, you're going to be within probably a good 3 or 4 thou or something like that if you eyeball it pretty good. So that's what I do whenever I definitely need to conserve my space, or I need to nest everything properly, but I don't want to go through the process of edge finding. So as of now, I am set up a little bit offset to the left-hand side of the HDPE planks, and I'm set up a little bit to the front, and that's fine for me because I'm just going to do an offset anyway. So I'm going to go to 0x, 0Y, and then I can drive this back a little bit. And one of the best parts about this machine is...
Can you show where you put the 0x and 0y?
Right. So if you click this button right here, 0x.
Where are you?
Right here.
Okay.
And then if you click this, 0y, it's going to zero out the different coordinates. And then I want to say, if I go back to machine coordinates, now instead of it being whatever it was, like 0, 0, 0 back there, it's going to give me different coordinates. So we're always, make sure you're not on machine coordinates. We're on the workpiece coordinates, I think. So we're at 0x, 0y. The last thing we need to do is we need to 0 the z. We just ran into a problem that you may run into, and we needed to find out what was going on. I don't know if we had a zoomed in version of what was going on the screen. We switched over by hitting tab to jog, and I think it had a whole lot to do with the fact that we had the pendant plugged in while we were doing this, and it gets a little bit confused. I choose not to use that if possible. I was just going to show it, so I leave it off and unplug. This is the USB that is attached to it. What we did is whenever we went over to jog mode, the cycle jog step or whatever was cycling from 0.0001 to 0.001 and then going through those numbers. And we couldn't set the particular step size that we need. And the step size is important because that jog, when we go over to the continuous, you go page up, it's unpredictable. So I might drive this down a 1/4 inch, I might drive it down 3/4 of an inch. It's variable. So I try not to do anything like that. I'm going to get it as close as I can within reason, and I'm not touching it. And then I can put the paper underneath, and I can switch to 0.1 millimeters. So you just hit or tap on the point or this cycle next to cycle jog step, and we're going to go from continuous to step. And then if we do that and we say, okay, well, if we went to 1, that should go up 1 millimeter. So we look at the Z and we say, okay, page up. And it went up 1 millimeter. So we'll go down, back to where we were, and then we're going to change the step size to whatever we think it is. So I'm going to do, I think, 0.1 millimeter, and then page down. And then for each one of the 0.1 millimeters, we're going to go down 4/1000ths of an inch. So you can see the step size in here. If that doesn't correlate to what you see on the jog mode or the cycle jog step, be very afraid because you might drive it into here. So we'll continue doing. It'll start dragging. And it's getting closer. I can feel it. All right. So now that we started dragging, that should be, I think 0.1 millimeters is the size of a sheet of paper. It's about 4 thou. At least that's what I'm told. You can measure it. Take it out. We're at 0.1 millimeter. If we go down one more, then we should be sitting right on the HDPE, which is where we want to be. So at that point, we can hit 0Z, and that's going to set our 0Z. Or we can do it the easier way if it's available at the time, because sometimes it acts up. Go to jog mode, continuous, drive it upwards until we get to wherever we need to be. And then we can take this guy and hold it down on here. Watch your hands. Usually an end mill is just really small, so you can just hit the very center of it. With these guys right here, the very edges stick down further, but we're going to go to the machine cord. I'm sorry, we're going to go down to auto tool 0, and then press it, and it's going to go all the way down. It's going to touch off on this because there's a circuit built into it. It'll travel back up just a little bit, and then it'll automatically set our 0. So now that we've set our X0, Y0, and Z0, let's make sure that All right, cool. So I can travel wherever I want, send it away. If I go to 0,
Where is it? Where is it?
oh,
Just in the screen.
all right. So page up, we can travel right here, underneath all of the XYZ. There's a go to 0, and we can hit that, and that's going to travel down, over, and then back down, and that'll show us exactly where our Z is. And if you're critical in where your space is, it's very important to know that. It's scary as hell because it moves downwards and then it moves over. Don't know why it does that. It should just move over and then downwards, but it be like that. So now we're where we're supposed to be in the corner. We're at XYZ 0. Saved all that stuff. Now we're pretty much done with this for now. The next thing that you need to do is you're gonna have to develop your NC code through whatever program you use. It's not, you don't have to use SolidWorks and HSM Works, but it's pretty useful in that the setup for it is the same-ish through Inventor, Fusion 360, and HSM Works through SolidWorks or whatever. So you're familiar with the tabs, you're familiar with the all of the operations. It's very predictable, and it still uses the same post processors. And the post processors are really important because you can take this computer, you can generate this cam. When you post process it, you can tell it, I want to put this on a Haas. So you can go down to the Haas post processor, you click that, it generates whatever G code the Haas sees. Perfect. I was like, all right, well, the Haas is down right now. I need to switch over to the OMIO. You go down to the OMIO post processor, same thing. So they've got a huge selection of post processors, and it's very user friendly. There's
This
a couple.
plugin specifically can have a lot of processors.
What's that?
What is this plugin specifically can have a wide range of processors for different machines?
Right, it comes with all of those.
Okay.
So we can choose any one of those. It'll actually prompt you for it whenever you go to post process it. The Roland up in MAB in the rapid prototyping room, the OMIO, Shipoko, Haas, any of these guys or whatever, they use, you can generate the G code that you need or the NC code for it to read. So that's why I like it a whole lot. It does lose a couple features like tabs and whatnot, which are pretty important, and I kind of wish they had it, but the trade-off is all of the cool stuff that I told you before. So I tend to use this over the integrated cam. So I don't use SolidWorks cam. So what we did is we're gonna set up a job for a arbitrary size of the spoil board, which is the HDPE that we have, so that we can face everything. So I'm gonna grab a tape measure, and I'm gonna measure the size of this. Probably could have done this before I sent the spindle there, but that's all right. So it's gonna be about 11 by 18. And we'll give it an offset anyway. So we can go into, so for this sketch, it's about 11 inches by 18 inches. So don't do that. And now we got about what the spoil board size is, and we can exit it. I usually use the same program for whatever spoil boards I'm using, and I can just change the dimensions. The size of it doesn't matter, like the thickness or whatever. So you just have to have some thickness. I gave it 1 inch. And then we can go over to our cam. And there's 2 different ways you can do this, through the pocketing operation or a facing operation. Pocketing, I could probably generate both and then show you the difference. But the way that I can do this, I'll just do it from scratch so that you can see it. So we'll do a new job. And this is all selected from what we did. You make sure it's all selected, and you can choose the particular workpiece that you're using and whatever zero you're going to zero off of. So right now the zero is at the very middle of the workpiece and it's at the top of it. If you wanted to do it a different way, like you wanted to zero at the very base and make sure that you never dig into the board, you could technically do that. I don't. I could drive it right into this HDPE, and I don't care because I can replace it, but I don't want it to screw up and go into the aluminum. That'd be a bad thing. So,
Wait, can you put the mouse on the other side of the pyramid?
yeah, or I could go down here.
Yeah. There you
So that's a little bit weird. All right. So now that this is in the very center, that's not where I want it, because as we just went over here, we put it in the corner of it. If you generate this G code and you tell it this, it's gonna go not where you want it to go, and it'll start your cut, probably run into some stuff and break some other stuff. So we're gonna go to, and all of these are pretty dependent on what you're doing. This drop down is your work coordinate system. I like to use the Z-axis and the X-axis, and then you can tell it what your Z-axis is, and I grab the top plane, and then for the X-axis I grab the front corner, and now I've got my X this way, I've got my Y this way, and I've got my Z this way, and that's how my machine's set up. If I were to choose not this, but I chose this guy, then that means I'm going to turn my whole workpiece sideways. I'm still going to go off the corner, but now it's going to do like lengthwise instead of into the board or whatever, like this way. So it'd be this way. I don't know, you can't see it, but so we want to make sure that we grab whatever edge that we're trying to go towards. This is still in the center. That's bad. So I'm going to go down to stock box point. It was already there. So if you notice that the X, Y, and Z coordinate system is in the middle of our workpiece right now, that's not where we set on our workpiece. So it'll start that cut in a different place than we intended. So what I want to do is I want to go to the work coordinate system and I like to use Z-axis and X-axis. For the face on the Z-axis, So for the Z-axis, I select the top face, and then for the X-axis, I select this front edge. And if for some reason you're sitting still in the center, you can go down to your origin, select box point, stock box point, and then you can go up to top corner 1, and that's going to send it down into the bottom left-hand corner, which is where I zero most of my stuff off of. So now we're solid on that. Don't worry about anything else under here. There's a couple other things that you can do, but this is a very basic introduction. And then what we're going to do is we're going to do a pocketing operation. Well, I showed you how to do that, so we'll go back up to here, change the stuff that was broken. So I did the face, the edge, you select this, and then this probably won't exist whenever you're doing your paths, but if you've already done it and there's a little X next to it, that means you need to regenerate your path, or if I have a problem with it. So we're going to click generate path, and it's going to try to generate whatever path is available. This is suppressed, so I'll try it again. Cool. So we've got two different options. You can do a pocketing operation where it starts at the center, or it starts over here and it goes around like this to the center, or the other way around. And there are benefits to that, but I really won't go into it right now. Or you can do a facing operation. That's its own, where it's going to start here, it's going to pass this way, go back, step over a little bit, and then it's going to go through. I'm going to do the facing operation because that's what it's designed for, and we can go into whatever the operation is and select what end mill we need. The good thing about the end mills in the particular computer that y'all are using is Jackson set up a pretty cool system of whatever material you're using and whatever size you need. It's all numbered and it's assigned to a certain tool in this library. So if I go to, it'll look a lot like, where is it? Go over here, see if I can find it.
So
We might need to cut this out. What's up?
This is in your computer, so you've imported all the tools
Right,
into
from
your computer?
him. Yeah.
Okay.
And on this one, I swear I remember it actually saying P whatever on it. I just don't know where it says it on here now. It was one of these guys. So, whatever. Regardless, it's set up, and you can actually choose the speeds and feeds automatically based on the tool that he's already. Are we good now?
Yeah.
All right. So on the tools that he's already assigned and set up for you, the spindle speed and the feed rate are there. So you just have to select whatever you need for the plastic, the aluminum, and then some of the other stuff. So that's pretty cool. And then if you wanted to play with the speeds and feeds from there, then you can dial it in depending on if you buy a new one. So I do, my particular one is a 1 1/8. For the end mill that I used was the facing end mill from Amana. I looked up their specs online and I found out that I need to rotate at this spindle speed at this feed rate, and it tells me I need to go at whatever 18,000 RPM, and then all of these are
in the tool specs from the manufacturer. It tells you if you're cutting X, Y, Z material, these are the speeds that you need. These are all the parameters that you need to put in there.
right. So all the good ones, the good end mill manufacturers will tell you chip load per tooth, or they'll tell you how much surface feet per minute that it can handle, and then you can go through the different calculations to back your way into the depth of cut, into the feed rate that your particular thing is, like the exact thing that you need to do. So Amana is a really good resource for that, and you can look up Amana end mills and then look up a 1/4 inch 2 flute for aluminum or something, and it'll bring up the chart to tell you 0.003 feet per tooth for aluminum, and then using that information and the surface feet per minute, you can figure out the rest of the calculations. You're gonna have to dial it a little bit because a lot of these guys assume that you're using some big boy mill, and it's almost infinitely stiff compared to the ones like this, which are great, but they don't stand a chance up against something that's taken off all sorts of material. So keep that in mind that you might need to dial it back a little bit, but Amana's pretty good about giving you the information that you need to back your way into the calculations you need. So for the spindle speed and the cutting feed rate in millimeters per minute, I like to not be in metric system for this, just because I'm more familiar with the how many inches per minute, and that's kind of what we learned in DML and stuff, so it's a little bit more intuitive. So I'll say that I want to do 18,000 RPM. The ramp spindle speed is whenever you're ramping into the material. Generally, I think it chooses the same thing when you do it. This is going to go really fast because I'm taking off very low depth of cut, so it's going to go about 200 inches per minute. That's what the big boy machines do with metals and stuff like that, so that's the difference. This is just going through plastic, and we're going to do the lead in and lead out is about 100, and then the rest of the stuff. So I'll make this available.
What is lead in, lead out?
What's that?
What does that mean? Lead
Okay.
in, lead out.
So there's different operations that you can approach the material. You can plunge into it, you can ramp into it, you can helix down into it, and then I believe your ramping is whenever you're ramping down into it, and your lead in is whatever approach that you're taking. So I think you're doing an angle down into it, you're leading into it, so you're not gonna want to, like, because you have some axial depth of cut compared to, instead of moving radially through your material, you're going to want to slow that down just a hair, and they'll also give you that, I think it's 0.2%, no, I'm sorry, it's like 20% slower or something like that. but they'll give you that through the manufacturer too. Or you can trial and error it. The lead in, lead out ramp, and then your plunge feed rate. I was just talking about how you can plunge down into something. Generally, most end mills hate to plunge unless they're designed for it. So mine is a lot slower. It's about 100 inches per minute. It's still pretty quick, but it kind of doesn't want to do this very often. So you want to try to either Helix in is one of my favorite operations, or some of the other options. But for plastics, things like that, it's not a huge deal. You can just go in and run through it. Aluminum, you have to be a lot more careful. So the next one is, we didn't have to select anything because it's a facing pass. It's just going to assume that we want to do the whole body of this. This section is tells you a bunch of the stuff about where your tool is going to end up whenever it's moving not in the piece, or what it's doing while it's in the piece. So with the mouse over, your clearance height is like if it's moving up and over, that's the clearance you have between the workpiece. You can minimize that whenever you do if you have a bunch of features and they're all, you got to get done quick, and you know that it's in like aluminum, or even I've cut steel on this, the amount of time that you spend moving up, over, and then back down, if there's a ton of features, it could end up saving you a bunch of time if you can dial that down a little bit. Generally, I don't mess with it because it moves pretty quick. And then you've got your retract angle, so it retracts. Your feed height, you can read all about these. Even the clearance height, I think I might have misspoke on that, but luckily it tells you everything about this, so you can see whatever you want for it. The most important ones that we're going to look at is, it's asking you what's the top of the workpiece and what's the bottom of the workpiece, or the top of the cut and the bottom of the cut. The top of the cut, always for my facing pass, I do from selection and pretty much everything else, and I'll click that top face until it populates. And then the bottom, I'm going to do from selection, same thing. And for this, I'll select the top face also. So both of them are the same thing. And then I'm going to shave 0.0, say 20 thou off. And that's going to be, I forget, it was like half a millimeter or something like that. It's almost exactly half a millimeter, because I think a millimeter is like 39 thou or something. So that should be sufficient depending on what you need to clear. If you're dealing with a piece that's been worked over multiple times, you might need to do more than that, like a whole millimeter, but you may want to do steps with that. So be aware of what your depth of cut is and what you can actually achieve. So this particular part is the step over, and that's going to be if I do one pass this way and it travels through, it's going to do some step over, whether it's half the diameter, whether it's a quarter diameter, and then it's going to pass back through. If you try to do a full diameter, you might get some ridge in between it. So at least if you have some distance between the two, you minimize that distance, then you're going to keep on running through the same piece. You're taking off less material every time, and you're going to get better service finish.
And that is regardless of whether you have a pocket operation or a
contour.
Or yeah. Mm-hmm.
So contours don't use step over.
Okay.
Pocketing operations are the only ones that have some type of step over, because they're taking away all the material that exists inside of there.
Okay.
Whereas a contour just goes down and it runs all the way through. It's the same thing with the
So
slaughter.
which one was the spiral one?
The spiral one is a pocketing operation.
That was the pocketing one.
Right.
Okay. And
So
the one that was like this?
The one like that is a facing operation.
Okay.
So I guess it's a special type of kind of pocketing operation. But it uses the same idea where you do facing and then you do a pocketing operation. One may or may not be faster than the other. I don't know. I don't really do pocketing for that very much, because I like to pass through the piece. But if you're limited on space and you have to use this whole workpiece, then you have to stay inside your bounds. So I do a pocketing to make sure that I can get the whole workpiece. You maybe do something for the sub or the boat or whatever, and you need to use the whole work area. You can't do a facing pass for that, because it needs to pass over and then come back. And if it tries to pass over, it's going to hit your limit switch and you're not going to get your cut. So you have to do a pocketing operation that's going to stop at the very edge of it and then clear it out, or you need to do something. So those are kind of the situational things that you need to watch out for. Generally, the pieces that I cut are smaller than this space, so I don't really have to worry about it too much, but those are things to be aware of. And then even with the passes that I run, a lot of them aren't depth critical. Most of them are, I'm cutting a bunch of holes, I'm drilling a bunch of holes, and I'm doing a contour on the outside, and then here's my piece. So this one that we're going to be doing today is going to have pocketing operations. However, it's not depth critical to the bottom. It's just depth critical from wherever I measured to down to the bottom of that pocket. So we're going to be doing finishing passes on that to make sure that we have that material taken off. Okay. All right. Cool. So this one, if you mouse over, it says, okay, 0.75 inches. I'm using a 1 1/8. 0.75 inches isn't the whole thing. About 3/4 or something like that. So it'll tell you the horizontal step over. By default, this is 95% of the cutter diameter. So you aren't doing a full diameter cut. However, I like to minimize, if I can, a little bit of the step over so that you don't have as big a ridge as possible. So like you don't notice it. You have a question?
Yeah, so if you've already input the diameter of the cutting tool, right? The computer already knows it. So how come you're doing it, like you're putting the step over in a numerical way rather than like percentage of like whatever the diameter of the tool is? Because you mentioned some percentage part.
Right. So that's just
This
kind
is
of
the way it is.
Yeah. So sometimes the manufacturer, and I don't know if it's by convention or something like that, they do a lot of percentages. So maybe it's just the way that this is treated. So you might have to do some calculation.
You would have to still have in mind the diameter of your tool,
Right.
To decide like how much step over you're gonna get
Right.
in a cut.
Right.
Okay.
Yeah. So you can do it. It actually, and SolidWorks is good this way, is you can put your tool diameter and you can multiply it by some number inside of here, and it'll give you whatever you need to. So if I want to do a 75% step over for a 1.125 inch times 0.75, hopefully it does that.
Or you're just doing it the math, like putting in an equation.
Yeah, it used to do that. So it'll give me 3/4 of my full whatever if I want to do half or something like that. So it'll do those. That's a very good point. Never really thought about that. A lot of times I'll see like I'll see a radius step over, and then I'll just say I know that I'm using 1/4, so I have to do 1/8 step over or something like that. But that's a great point. I didn't actually consider
Just keep
that.
in mind the diameter of the tool. when you're
Right.
putting the step over.
Right, it's very important, and you can also have some offset to your tool. You can tell it's actually smaller than it used to be because I've taken off material from it over time, or it's designed that way or something like that. So you'll end up with a smaller cut than you need to. So maybe it compensates for that. I'm not entirely sure. The next one I don't really mess with. It'll give you the mouse over for it, pass direction. You can rotate it depending on what direction you want to come at. This is important, and you don't want to do like, if you're doing wood and you don't want to cut like with the grain, then you can go across the grain, or you can go like perfect, like in a different direction. So that might be an operation where you need to do it. Or if the material that you're using is directional and you want to travel in a perpendicular direction and your workpiece can't be set up that way, then you can offset the angle to compensate for that. I never do it because we don't really use very many directional things. This is where I do the pass extension. That's the offset that I was telling you about. I'm going to do 0.25 inches over, and that's just going to extend it. In every border, it's going to go an extra 0.25 inches, so I know I'm clearing everything in here. And then, what is this? Stock offset. I think that's where it goes regardless. So, oh, true. All right, so back it up a little bit. There's two different things. This one is how far I'm going to pass it in just this direction. In this direction. But if I do 0 here, and then I do 0.25 here, that's going to extend my offset all the way around this way and this way. So it starts earlier, it ends later, and then it goes past in both directions. And I like to do that when I'm clearing my material, when I'm doing a facing pass, so that you don't have ridges left over, because that can be problematic. You can do multiple depths. If I needed to take off, if I did a facing operation and I have to take off a 1/4 inch from some 1/2 inch piece and I'm using aluminum, you'd still do the facing operation, but you do what, 30 thou depth of cut or something like that. You would tell it to do a certain amount. So if I went to multiple depths and I say I want to go, I don't know, something silly like 0.001 or whatever, I can show you the difference between the two. The rest of this stuff I'll go back. The rest of this stuff I don't really mess with. This tells you which direction you're coming in. If you want to run through your piece, you can do it from both sides and in both directions, so it just goes zigzag through the whole thing. It's probably better to travel in the right direction, so that you're doing climb versus conventional, whichever you prefer. And then the last one is how I want to enter the piece. So this is where that stuff comes in, the lead-ins and the lead-ins and lead-outs. So it goes in like this, and then it starts moving through the piece. It's going to give you a little extra on the side whenever it cuts into it, but it's better than just plunging straight into it and going through your piece. Sometimes you don't have enough in your work piece to actually do that. It's very tight, so you do have to plunge into it, but you're going to sacrifice stuff for that. The rest of the stuff I don't really mess with. So let's generate this. And then if we go real close, that's because I did like 0.00, like a 1/10 of a thou or something like that. So all of these are going to be passes if I wanted to be silly. Out of the whatever 40 thou or something like 20 thou that I was taking. So I can go back and change this to not multiple depths. And if I look at it from the side, you can zoom in and you just see the one pass that it's going through, and it's going to take off that much. So that's what we're going to want to do for the plastics. You can do it for like wood and all of those things, but depending on what surface finish you want to do and what material you use, and that's what's important. So facing pass, we're going to suppress this. And then if you're working on the computer...
No, you're suppressing the 2D pocket, not the facing part.
Right, because I want to do the facing operation. So depending on what computer you're working on, if you're generating this on your computer and you want to take it over and plug it in, you can use your thumb drive. All right, so what we're going to do is, depending on whatever computer that you're using, if you're generating everything on this computer, which is kind of slow, it's going to take a while. But if you're doing it on your computer and you need to swap, take your NC code and put it over to the other computer, we're going to go, make sure you click on whatever operation you're on. We know that our tool is what it needs to be. It's a 9/8. We know it's a facing pass. You can see what the work coordinate system is, and then you can see some of the other stuff. So we're pretty good on that. Just in case, we have a note that says that we need to be in millimeters. If sometimes there's weird conversions between the two, and the controller freaks out when you give it inches and millimeters. It can't see whatever it is. So I make sure and I go to millimeters, kilograms second, regenerate it before I transfer it over.
Well, and fill it out in millimeters, and of course, you fill it out in inches, that goes in because the machine doesn't.
Right. Because I can't, in my mind, I can't predict like 625 millimeters per second. Like, I still don't know what that is. Right. So, okay. I'm sorry, man. I'm sorry. So we've got this facing pass, and we can go we do the generate toolpath, which it tells us we probably don't have to, but I want to make sure. And then we hit post-process. So this is where we select whatever machine we're going to send it to. If you're using another computer and you're using HSM Works, you're going to choose, or even on that one, you're going to choose Mach 3 mill. There's a bunch of stuff in here, all sorts of places. You can, I mean, all sorts of places.
So this is where you would pick, oh, I'm using this Haas machine, I'm using this.
Right.
OMIO machine.
Right.
Okay.
So they've got, I mean, they have all sorts of stuff. Siemens or
Wait,
Siemens.
you didn't download. This is given by SolidWorks, right?
Not
No, it's a
SolidWorks.
plugin.
So this is a plugin.
Oh, this
So
is a plugin.
HSM Works comes from, it's an Autodesk product. And for us, it's free. For all students, you can download a HSM Works Pro or Ultimate or another version. I think I'm using Ultimate.
Okay.
And those do, I think, have to be compatible in your years and in whatever model you're using. If you're going to transfer G code from or NC code from somebody else's stuff to mine or CAM software. So if you bring over something and you say, okay, I want to do Mach 3 mill, or yeah, see the like Haas is up here, and then if we want to go to multicam is what I've used before, and then Mach 3 mill, this is going to tell it this is the particular syntax that this controller uses, and follow all of these instructions. You can name it whatever you want. We'll do face, and then a lot of the rest of the stuff, like you could open up the NC, alter it a little bit if you wanted to give it special code instructions to go somewhere first or whatever, but I don't do that. And then the particular NC extension that it uses for this one is .tap, and that's important because if you post-process to the wrong thing and you say .nc or we'll cancel this out too, but another machine, you can't accidentally send a Haas to here and then it gets confused and it just runs into whatever your workpiece is or something like that.
So that in theory is linked up with whatever specific machine you've selected from there. So like you wouldn't have to edit it, or do you have to manually?
You do not have to.
Yeah. So
Yeah.
the program.
Most of these are already in there and you don't have to change anything. It knows that G23 is this, G31 is whatever this is. That might mean something completely different on another machine. I haven't really run into that issue before. I've dealt with, I think, 5 or 6 different machines at this point. It's been pretty good about having the code for, or the post processor for every single one of them. So that's pretty fantastic. So we call it face or whatever you want to, and then we can post process to our drive, and we'll create a new folder so that we don't get confused. And then we'll say this is going to be TPEG, and then save that. So now that's saved, it's going to be in there. When we transfer it over, we can run that path. I don't want to do this twice or whatever, so what I'm going to do is close this out, save everything, and then this is the other operation that I'm going to run. And it's a 1/4 inch aluminum plate, and we're doing a couple different operations, a pocketing operation, a contour, and an adaptive operation. The pocketing is the same thing that we talked about before, where it has some step over. There's a lot more lines here because this is aluminum, and we're going to be using a 4mm O flute. And the contour is also going to be not full depth of cut, so you can see the passes that are going to go down like this. So that's going to do the outer contour. And then because I'm going to switch to an 1/8 inch to do the very corners of it, try to get at least some semblance of the angles that they needed from the inside. On the outside, I'll be able to hit 90s, no problem, but on the inside, you have to think about the radii. So I use a smaller end mill if I can, and then since I'm doing it anyway, I'm gonna go ahead and set this up so that I can do the last like 4 thou depth. And that 4mm O flute looks a lot like this, this is 6mm, but it's a lot easier to see. It is pretty aggressive. When this tears through, this way.
Perfect.
All right. So whenever this goes through the material, it tears through, and it ejects those chips and big old chips. But when it comes to a tip, this isn't flat on the bottom like some of your other end mills. This is better. Some of your other end mills are like 3 flutes. Oh, all right. Some of your other end mills are 3 flute and they're flat on top. So whenever I do facing passes, that's going to clean up all of those lines. Whereas this is like a ridge and it would leave, I'll do some step over, and as it does that step over, it's not gonna get all of the material in between. So I'll do a finishing pass with a 1/8 inch, but it has a flat top, and I can get the rest of the ridges off there. And in the meantime, since I'm doing the corners, I'm gonna go ahead and throw a finishing pass on there, and that'll take off the last like 1/4 thou off the bottom, which isn't much for the 1/8 inch. So it'll serve two purposes. So that's what the two operations do, or the last operation. This adaptive is good because it considers a lot of the things that, it takes into account a lot of the heat that we would normally take for granted if we were moving through the material. So it'll move up and then go over to some other place, so it can leave a lot of that material, let it cool down while it's doing it over here. So effectively it's going a lot faster. You can go a lot faster through the material by doing your tool paths smartly. So we have a pocketing operation with a 4mm, we have a contour, and then we have an adaptive. Might do another video or something like that showing the differences between them and how to select the things, but the basis of everything on these at least is, we knew what the first pane was from. The second pane, I selected the outer edge, and then the rest of these are just modifying the things that I needed to do. Luckily for this, I think I went from the top to the bottom, and I gave it a 39 thou manual step over, which I forget what percentage that is of 4mm, but it might be a quarter or something like that. And then stock to leave, I said I want to leave stock to leave radially for 5 thou, and then axially 5 thou, so that I can come back through and clean up the rest of the material with the 1/8 inch. So that's kind of like my finishing pass operation, and the rest of the stuff is how I want to enter the material, what I want to do whenever I'm transitioning in. This one is your Helix, and that's going to give you you can see all these, but the Helix is going to helix down into it, which is what end mills like to do, and then it's going to start moving through the material. You have your maximum step down and a bunch of these other things, and then how big your Helix needs to be to get through those things. So we're going to select OK, and then your contour is going to go all the way around the outside. That, I just did the same thing. We'll cut that out. That's Nick over there. He's working on the go-kart. So the pocket, contour, the adaptive, so that's going to take care of the rest of the stuff and then clear up all that last material that I have.
So question,
Yeah.
for the adaptive one.
Right.
So basically you're telling me that the adaptive, the last step is to get the last part of the, like, the last layer, the last pass, right?
Right.
The finishing pass, and then also since you're using a smaller end mill, you're gonna be able to get a smaller radius on those corners that are in the specific parts.
Right.
In the specific, like,
Right.
pockets.
Right. Because I could do, if I suppress this, and this is actually a pretty good operation for anybody that wants to look through the cam that they did. They can do their pocket and then their contour, and you can go up to job and then do one of the two. We can do stock simulate, and then if we go to play it, this will give you what's left, and we can see there's this edge right here that's going to be left, and then the same thing is whenever it travels through here, it's pretty good about getting that material. But when you get to these edges, you got this giant radius that you have from the old stuff. And the same thing, I think there was another, there's a Keyway, right? So the Keyway is hard to see, but there we go. So this Keyway is supposed to be like square, and it isn't. And we're not going to get it square because we don't have a broach or anything or whatever, and I don't have the right tools for it. So what we're going to do is we're going to come back with that 1/8 inch and at least make it a little bit more reasonable. So you can go through and do your simulate and your stock simulate to find out what that operation does. And then I think I selected just the, yeah,
So in there, you also specified the amount of the distance in between your desired feature and where this thing is going to be, right? Because you're giving it a wiggle room there, just so you can have that last operation, right?
Not in here, or what? I don't
No,
understand the question.
In your toolpath or
Right.
in your selection.
Right. So this material right here is going to be smaller than the stock that we're going to be using. So the outer contour is just going to move all the way through the material. And that's what I like to do, is I like to define the outer edges by just cutting them instead of trying to go off of some of this material. I don't know for certain that this is flat in almost any direction, because it could be ground off. If you look, this looks like it was bandsawed or sheared or something like that. So you can never really guarantee what you need to do. And if you have to indicate off of this afterwards to do any specific features, good luck with that, because it's going to be different from here to here to here to here, like GD&T type stuff. So I give it this. We oversize this particular material when we get it. It's a little bit of waste. I'm all right with that. If I can verify that my operations are going to do what they're supposed to do, and it's going to end up the way that I want it to end up. You can buy precision ground stuff. You're going to pay a lot of money for it. So it's better off, in my opinion, for this particular scenario, to just oversize it and then repurpose the rest if you can. So we've got a pocketing operation, the 2D, and then the adaptive, we suppress that. So if we unsuppress that and we generate the tool path, and then we go back to stock, and we play it.
So the 2D is for the contour, for
Right.
the outside.
Right.
So now we're in the 2D operation.
We've done.
Or we did it already.
Yeah. So it,
Okay.
it did all of these. So you can see
The blue edge would be the
Right.
what the part would look like.
So this, I don't know if it's going to go over here, but this guy, if I can move it. I'll just let
It's
it run.
fine.
So yeah, and then the last part is it's going to clean up whatever the end of it is. And this was I was still generating. That's why I didn't do it. So you can kind of see how it's populating. It's pretty cool, mesmerizing, like a little backdrop. So some of these operations, why I choose to use a lot of 3D stuff or 2D stuff is because the 3D adaptive is kind of thinking through the operation and figuring out which places I want to be at what time. Whereas the 2D is like, I don't care, I'm just going to move through it. And it generates a whole lot faster.
So in this case, you have quite a small step over. It seems, or that's just like a usual looking part.
So this only has a small step over because it's an 1/8 inch. The other one is a 4mm, so I can do I have to do a less aggressive step over because
Oh,
it's
an
a lot
1/8 inch.
smaller. 1/8 inch cutter. So I'm going to swap my tool from the 4mm to 1/8 inch, and 1/8 inch is 3.125 millimeters or something like that. But the O flute can clear material a whole lot better. So the trade-off is what I said, like the facing operation. I don't generally use 1/8 inches that much. There are 1/8 inch O flutes, but I really like the 4mm. So this one's still generating because it's thinking, but it actually moves around the stuff. So we'll let that generate while we talk about broken end mills. So I've got 2 examples of what happens whenever you get your speeds and feeds wrong. One of them is if you move through the material too fast. Up. All right.
Pin it down.
Down.
Yeah.
All right. One of the ones is you move through the material too fast, and this used to have a top part to it. Forward.
Up, down. I'm sorry. There you go.
All
There.
right. Somebody's gonna edit this out.
Yeah, there you
All right. So freeze. All right. So this is this used to actually have I think 32 thou or something like that sticking out of it. It no longer exists like that, so I don't even know what it's good for anymore, but it's a good learning idea for people. So that's, you move too fast through the material, breaks your end mill, not a good idea. Hopefully the stuff is pretty much cheap. These are all fairly cheap end mills. This one is Harvey Tool, that's a lot more expensive, but this one is a 3 flute that built up too much heat, and then it generated chips that just couldn't evacuate, so they're stuck in the flutes, and it made it essentially worthless. Until the pro tip or whatever, you can use lye. If it's a carbide tip or a carbide end mill, you can use a straight up lye from bathroom cleaner or something like that. And if you put it in, it eats away the aluminum. It will also turn your skin to soap, I think, because it's a base, like one of the basiest bases there are. So be careful with that, but it can do a lot of pretty cool stuff with cleaning up your end mills, and then they might still stand a chance. If you destroyed them, it happens. You get my other ones. So this is fully done. Adaptive is good. We can go to see if this did its stock simulation, and then now it's got this piece right here, it's got this guy right here, and then the last part is it's going to do that step over. Because we want to get the very corners of it, we could do some, if we didn't do the facing pass, if that wasn't important to the customer or whoever we're making this for, then, and you just wanted to make sure that the corners were rounded off, you could just not do the stock to leave on the bottom, and you could leave stock to leave radially, or you can clear all that material, and then when you do 3D adaptive, if everything is cleared and you follow it from the previous job, it'll just take off that corner and you're good to go. So I like to do finishing passes this way if it's important. So we did stock to leave, and then let's see if we can get over here. This guy, we might just have to play it.
Yeah, play.
There we go. All right, so once we play it, then we can see that it's a little bit rough, but this was the piece that we were trying to get. We no longer have the stock that we had to leave there. We've cleared this material and we just left a little bit of this material, which is sufficient for, I think, what we're trying to do. So
Why does it look like that? Just rendering?
probably. There's probably a thing that I can make it look prettier. Yeah, so, but you can take it, you can make it look, you can take a look to see if the corners are doing what you want it to do. And it's always good to preview the stock simulation. And if you want to do the simulate, that'll show you the tool path, and you can play it and watch all of your operations happen. See if it does anything funny. Once you run this operation, it'll actually tell you if your collet runs into the workpiece. If I'm trying to cut through 1 inch and I'm using a stub of a 1/4 inch or something like that, and you define your collet and your holder, or if you're doing your work holding, you can define like your vise or something like that. It'll tell you when you crash.
So you can input the size of the collet right there.
Right. So I can make this, and in fact I have made it before on the other ones. I could probably show you an example, and you can see the size of this. You could even make a lot of this, like recreate this, so you know exactly what you're kind of looking for. You could make this and know that you're not going to crash into it. You can know that your workpiece, if I tried to drive this down into here or something like that, there'll be a nice crash going on. So
basically, if you were to be cutting deep enough, then you want to consider where the collet is, so you don't ram into
very
your
much
piece.
so. And that's going to determine, that's going to determine which cutter you use. If I use a giant cutter like this serves a couple different purposes. This is longer in that I can go through a 1-inch piece of material, and it has 4 flutes, so I can give it a facing pass. This is basically your finishing end mill, whereas if I do something with a 6mm and the flute length is only, I think, 12mm, then I only have 12mm to go. Like, you can't clear, if you're all the way down into the material, the chips can't go anywhere.
But this one's more rigid, so you could
Right.
run, I guess, at faster speeds maybe?
Much so, yeah.
Okay.
Yeah, so that's the trade-off that you would have with some of these silly small ones, like this one and this one. So this is really small, and you can go deep, and you can cut just a little bit if you're going through some shim stock or something like that. The same thing with the 4
So would you secure it somewhere in here, and then have all of this kind of as you're cutting?
You can do either one. This is relieved in here so that you can go down even further if you wanted to. This is designed for like extended reach, so you're going to increase your cantilever and you're going to have more deflection as you move through your material. You could grab it deeper in there, but that particular spindle has a limit to where you can push it down. I don't know what it is, but it might limit it here, and then you can't go very much. But this is designed so that you can grab onto up here, still have a little bit if you need to do deep cuts, but very shallow at a time. So it's a specialized tool. Same thing with, this is an 1/8 inch O flute, and this is very short. I would use this to cut through very small material, but I would try to chuck it up as far up as I can, so I'm grabbing it basically as close to the flutes as possible, where I can get chip clearance, but I can get the maximum rigidity through the material, so I can just drive that thing through the aluminum, whatever it is. So that's what the benefit of these smaller ones are for, but you're only going to go but so far into your material with this particular end mill. All right. So at this point, we've already gone over our CNC. We've gone over some of the tools that we're using. We went over the tool paths and some of the things to look for. There's a lot more you can go into in choosing your tool paths, how you do everything, how you enter it. This is a very basic overview. Doesn't kind of seem like that, but this is how to operate the machine. Now that we do that, we did the simulation, stock simulation, and we did the regular simulation. If you had an automatic tool changer, which this machine doesn't, then we could just assign whatever tools these are, and then it would go down, grab whatever, go to the next one. Unfortunately, we're not in that situation. It's still a great machine. We do manual tool changes, so the easiest way for us to do this is we just save these operations, this one and this operation. They use the same end mill. We're going to post-process just those two. And then we can go back to our Mach 3 mill, name it the...
And just those tools because you're using the same tool.
Right. Because it's the 4mm for both of it. It doesn't have to change, whatever. And then we can do 4mm. And then post-process that into a million folders. TPEG. Save that. And then now that's post-processed. And then this is my 1/8 inch. So I can go back up here. Oh, I'm still in inches per second. Is that where you're looking or no?
No.
Okay.
I was looking.
So let's go to good not, I don't know how to, is, I went to millimeters, kilogram seconds or whatever, and let's do that again, just for the sake of sanity. And we can go back down to USB, TPEG. This is going to be our control panel 4 millimeter. We're going to replace that. One sec. Okay. So at this point, we've generated the 4 millimeter, the 4 millimeter. We made sure that it was in millimeter, gram seconds, kilogram seconds. It doesn't matter. But as long as we're away from inch per second, because the warnings on this machine, according to the person who bought it, said that we need to be in millimeter. So we'll do that, and then we'll go to the 1/8 inch. Still in the same thing, but we can post-process it. We can name it 0.12 or so 125, and I'll just remember that. Probably come up with some convention that you need to, and then we can save that into there. So let's make sure we got everything. So we have the facing operation, we have the control panel for the 4 millimeter, and we have the 125. So let's eject this. If it doesn't yell at me, all right, cool. And then we can switch over to this computer. We're going to put all the safety stuff back. Our first operation is going to be the facing operation. Oh, good call. We've already done our 0. But
Do you think maybe temporarily we can leave that one for this trial?
yeah, I mean, that's not going to hurt it.
Plastic, yeah.
Yeah.
We'll all wear glasses.
Yeah, that's a good call. All right. So, now that we've zeroed off here, and this up here, this is for the air nozzle and the fluid that we're going to go through, and that's going to happen whenever we do the aluminum. We can turn on the compressor. And this is for chip clearance. If you don't have this on, it can be really hard to run the speeds and feeds, and you'll have chip buildup, and you'll probably end up with the same thing that's happening with that 8 millimeter. So I do that. We'll point it at where it is, and then this is not going to be that loud. When it gets to the aluminum, we can put on our headphones or our earbuds. We get a file, load G-code, and then go to why is it not forward?
We're running a case.
The camera was closing.
It's fine, it's fine. You're good.
Yeah?
Yep.
All right, so we got the facing operation. We knew that it was at the top. So we can go to, make sure this is on. That's how both of these are on. We already did this stuff, we're good to go. And then we can go to our facing operation. If we're gonna open that up, it's gonna populate all the G-code over here. And that's gonna tell you all of the stuff that it needs to do. It's a pretty simple operation. So we'll go to cycle start. It's gonna move up and then start spinning once I hit the cycle start. So basically we cleaned off the material and any waviness, flat. We wanted to ensure our flatness to a certain degree. So we used that 3-flute spoil board surfacing. And this is what would be called a spoil board. And then the baseboard would be underneath it. And these are aluminum extrusions. You don't want to dig down into it. So we had to make sure that we could step over. This is fairly straight. The spindle may not be perfectly perpendicular to the baseboard. So if it has some angle to it, you're going to be left with a little bit of a lip, a ridge or something like that. It's acceptable to 99.9% of people. For the people that aren't, we need maybe something different. I've done aluminum before. This in particular, so I've used this as my spoil board. If you need to ensure flatness and you want to run over it with your end mill, I'll take a 1/4 inch. It'll take a lot longer, but you're being more stiff. You are doing less of a step over, so you're going to see maybe more of these ridges, but they're not going to be as pronounced. And then, I mean, you can see how shiny the surface finish is, so that turns out pretty good. So if flatness is critical and depth of cut is critical to your operation, you might have to work with your work holding a little bit. You might have to work with whatever spoil board you're doing. But for this operation, we're just going to put down this piece of aluminum, 6061. On top of here, we have that outer contour, so it's not going to worry about any of the outer edges. It's just going to dig all the way through it. And then for the pocketing operations, according to the person that we're making this for, it's not as critical as, you know, I need to be within half a thou. So we're going to do as close as we can to it, but you just need to ensure to whatever workpiece you're working with or whatever design that you're having, what type of expectations you have. And if you have more expectations than your machine can offer, you might need to consider where you're getting your work done. But for this, it's very effective for quick cuts, for reasonably accurate and precise cuts. I don't know what the plus or minus is, but pretty darn good. So what we're gonna do is we're gonna probably take a little bit of sandpaper and just get rid of some of those ridges. That's gonna shave off some of the extra stuff. So there's some of this. And just get the very, almost nothing. The part that you need to more worry about is kind of the edges. Those kick up a lot whenever it's going through. So I would hit the edges. Unless you were just going to the very inside of the work or the spoil board, then it wouldn't matter for the edges. So we're going to take a little bit of alcohol, which is right here. Don't drink it. And then we're going to grab a rag for you, please. Right. All right, so we use the activator on the other side. We put the glue on the one side. It's not fast drying. So while that's drying, we can change the end mill. So we can drive this through here. We have to change out the collet. Just in case you're by yourself, you don't want to break your end mills, put it above something soft, so in case it pops out, you don't shatter it. It doesn't do weird stuff, remember. basically go this way. So put our end mills back. This is the 1/4 inch, and if we had a 1/4 inch, we could just swap it out, but we don't. So we're going to use the 4mm, which was right here. Make sure that goes, and then we'll grab a new 4mm. And don't forget the collar. Try to put it as far up in there as possible without getting too crazy with it. The collet nut actually sticks down a little bit, so you can kind of feel that out. But we want to give it a little bit of room to evacuate. So I don't know if you want to look at that, show them what it looks like.
I don't know if I can.
Yeah. So
No.
basically what we're doing is we're going to bring it down to about right here, and that's about as close as you want to go, because you want chip evacuation, and you can't really get chip evacuation if you're blocking some of it. And then you also don't want to clamp down onto the flutes, because that's bad for everything. So that's where we are with the 4mm. And we're no longer 0 to Z, so remember that, recalibrate your Z axis. You need to make sure that the piece was, how wide was the piece?
7 by 10.
7 by 10. So always check your piece. I'd probably leave this open. That was a mistake to not do that. But we need to make sure that this has enough space, and we definitely do. We definitely do. So if we needed to go over the 7, we could still rest on top of the HDPE, so we're not pushing down into a cantilever or whatever. It's best to try to conserve material as much as possible. We could have done a 0, or we could have moved this over and been a little bit more smart about it, but be like that. So we're good on our X and our Y, pretty much right there where it needs to be. All right, so we made sure to verify that the thickness is whatever it was supposed to be. We made sure to verify that the thickness was whatever it was supposed to be, and we altered that inside the SolidWorks model, so we know that we made it all the way through. That's something important to negotiate, because if it's too big, then it's going to think that it's going to go all the way through there, and you don't want that, or even further down into it. If you accidentally put a 1/2 inch piece, but you have 1/4 inch stock, it's going to go past by a 1/4 inch, and that's going to be bad. So we know that's good. We would normally run alcohol, but it's acting up right now, so we can run air for just the time being. The speeds and feeds are pretty good for either one. It'll just do better chip evacuation, cooling down everything if we had alcohol. But so we're going to start it. We already did our 0, and we'll see what happens. Ready to go?
Wait.
So what we did is to keep it from moving, so that we could swap whatever we need to check something out, make sure everything's good. There's a feed hold section, and we can hit feed hold. The second button on there is the yellow one, and then we can go back to cycle start to make it go back through. We don't want to hit stop. Sometimes when it stops in the material, it's really hard because it's continuing to move, and then it stops and it binds up. So we'll go back to cycle start, and it'll continue moving through.